Welcome to DAR Tutors for online and home tuition. In this video, aligned with the IB Chemistry Higher Level curriculum, we will explore the fundamental concepts of measuring enthalpy changes. By the end of this session, you should be able to, first, understand the distinction between heat and temperature. Second, differentiate between endothermic and exothermic reactions and interpret their energy profiles. Third, apply the quantitative equations for heat transfer. Q equals mc delta T and enthalpy change, delta H, to solve chemical problems. And finally, analyze calorimetry experiments, including interpreting data with cooling curves and calculating uncertainties. Let's begin by clarifying two critical terms: heat and temperature. Heat is the form of energy that is transferred between objects with a temperature difference. It's a process of energy transfer driven by the movement of atoms and molecules. Temperature, on the other hand, is a measure of the average kinetic energy of these particles within a substance. A higher average kinetic energy means a higher temperature. Think of it this way. Heat is the act of energy moving, while temperature is a state or property of a system. When a hot object is placed with a cold one, heat energy will transfer from the hot object to the cold object. This transfer continues until both objects reach the same temperature, a condition we call thermal equilibrium. At thermal equilibrium, the average kinetic energy of the particles in both objects is equal. In summary, heat is the transfer of energy between objects due to a temperature gradient, while temperature is a measure of the average kinetic energy of the particles in a substance. Now, let's connect these concepts to chemical reactions. When a chemical reaction occurs, energy can be either released to the surroundings or absorbed from them. We classify reactions based on this energy transfer. The law of conservation of energy is fundamental here. It states that energy cannot be created or destroyed, only converted from one form to another. In chemistry, we focus on the energy transfer between the system and the surroundings. The system is the part of the universe we are studying, typically the chemical reactants and products. Everything else is considered the surroundings. A useful analogy is a bank account. A chemical system has an internal energy, which is like its bank balance. When the system releases energy as heat to the surroundings, its internal energy decreases, like making a withdrawal. This is called an exothermic reaction. The temperature of the surroundings, like the water in a beaker, will increase. When the system absorbs energy as heat from the surroundings, its internal energy increases, like making a deposit. This is an endothermic reaction. The temperature of the surroundings will decrease. You can always determine if a reaction is endothermic or exothermic by observing the change in temperature of the surroundings. If it gets hotter, it's exothermic. If it gets colder, it's endothermic. We can visualize the energy changes in a reaction using a potential energy profile. A potential energy profile shows the potential energy of the chemical system on the y-axis and the reaction coordinate, or the progress of the reaction, on the x-axis. Here is the profile for an exothermic reaction. The reactants start at a high potential energy level. As they react, they form products with a lower potential energy. The difference in potential energy is released as heat to the surroundings. So, in an exothermic reaction, the system goes from a higher potential energy state to a lower, more stable one. It releases the difference in energy to its surroundings. Conversely, for an endothermic reaction, the reactants start at a low potential energy level and form products with a higher potential energy. The system must absorb energy from the surroundings to reach this higher energy state. Therefore, endothermic reactions involve a transition from a lower potential energy state to a higher, less stable one, requiring an input of energy. Let's apply this. Draw the energy profile for the combustion of sulfur, which is an exothermic reaction. Since the reaction is exothermic, the potential energy of the products, sulfur dioxide, will be lower than that of the reactants, sulfur and oxygen. The graph would show reactants at a higher energy level and products at a lower energy level, with the difference representing the energy released. To make these energy concepts quantitative, we need a way to calculate the heat energy transferred. For a pure substance, The heat energy transferred Q can be calculated using the equation Q equals mc delta T. Let's define each variable in this crucial equation. Q is the heat energy transferred, measured in joules, J, is the mass of the substance undergoing the temperature change, measured in grams, G. C is the specific heat capacity of the substance, a unique property that tells us how much energy is needed to raise the temperature of 1 gram of that substance by 1 Kelvin or 1 degree Celsius. Its units are joules per gram per Kelvin. And delta T is the change in temperature, calculated as the final temperature minus the initial temperature. You can use Kelvin or degrees Celsius here, as the size of a 1 degree change is the same for both scales. Now, let's work through an example. Calculate the heat energy required to increase the temperature of 20.0 grams of nickel from 50.0 degrees Celsius to 70.0 degrees Celsius. The specific heat capacity of nickel is 0.444 joules per gram per Kelvin. First, we list our knowns. M is 20.0 grams, C is 0.440 joules per gram per Kelvin, and the change in temperature is 20.0 degrees Celsius. As we discussed, this is the same as a 20.0 Kelvin change. Now we substitute these values into the formula Q equals mc delta T. The grams and Kelvin units cancel out, leaving us with joules. Performing the multiplication, we find that Q is equal to 176 joules. This means 176 joules of heat energy are needed to raise the temperature of 20 grams of nickel by 20 degrees Celsius. Beyond just heat energy, chemists are deeply interested in enthalpy change, symbolized as delta H. The enthalpy change of a reaction, delta H, represents the heat transferred at constant pressure. This is a very common condition in the lab. It's important to differentiate this from the change in internal energy, delta U. At constant pressure, the system can expand or contract, doing or having work done on it. Therefore, some energy can be converted to work instead of heat. The relationship is given by the equation H equals U plus PV. Under constant pressure, the change in enthalpy is the change in internal energy plus the pressure volume work done. However, for most reactions in solution, the volume change is negligible, and delta H is essentially equal to delta U. When gases are involved, the P delta V term can be significant, and we use the ideal gas law to express it as delta nRT, where delta N is the change in the number of gas moles. Crucially, for our purposes in calorimetry, the heat energy transferred Q and the enthalpy change delta H are related by delta H equals negative Q. This negative sign is critical. Q is defined as the heat transferred to the surroundings, whereas delta H refers to the change in energy of the system. So, if the surroundings gain heat, Q is positive, the system must have lost it. Delta H is negative, indicating an exothermic reaction. Let's summarize. For an endothermic reaction, heat is absorbed, so Q is negative for the system, and therefore delta H is positive. For an exothermic reaction, heat is released, so Q is positive for the surroundings, and therefore delta H is negative. Most enthalpy change values are given under a specific set of standard conditions to allow for fair comparisons. This is called the standard enthalpy change, denoted by the symbol delta H naught. Standard conditions are not the same as standard temperature and pressure, STP. Standard conditions for thermodynamics are a pressure of 1 bar, which is 100 kilopascals, a concentration of 1.0 moles per cubic decimeter for any solutions, and a specified temperature, most commonly 298.15 Kelvin, or 25 degrees Celsius. The standard state also implies the most stable physical state of a substance at these conditions. For instance, water's standard state is a liquid written as H2OL. So when you see an equation like 2 hydrogen gas plus 1 oxygen gas gives 2 liquid water, with a delta H naught of negative 572 kilojoules per mole, it refers specifically to the reaction occurring under these standard conditions. Notice 2 key points about this notation. First, the physical states are shown in parentheses, like G for gas, L for liquid, S for solid, and AQ for aqueous. Second, the delta H naught value is given in kilojoules per mole. This indicates the enthalpy change for the reaction as it is written in the balanced chemical equation. So, 572 kilojoules of energy are released when 2 moles of H2 react with 1 mole of O2. This per mole unit is crucial. It means the enthalpy change scales with the stoichiometry of the reaction. For example, if we were to reverse the water formation reaction, forming hydrogen and oxygen from liquid water, the sign of the enthalpy change would also reverse. It would be positive 572 kilojoules per mole. If we were to write the equation for 1 mole of water, we would have the stoichiometry and, consequently, have the enthalpy change, giving 286 kilojoules per mole. Understanding this relationship between stoichiometry and enthalpy change is fundamental for solving more complex thermochemistry problems. We can now combine our knowledge of Q equals mc delta T and enthalpy to calculate delta H naught for a chemical reaction using experimental data. The general formula for standard enthalpy change of a reaction, delta H naught, is delta H naught equals negative Q divided by the amount of the limiting reactant in moles, all multiplied by its stoichiometric coefficient from the balanced equation. Q must be in kilojoules for delta H not to be in kilojoules per mole. A common mistake is forgetting to convert joules from the Q equals mc delta T calculation into kilojoules for the final delta H naught value. Always remember to divide Q by 1000. Let's apply this to a worked example. When 0.025 moles of sulfuric acid react with excess sodium hydroxide, the heat energy change, Q, transferred to the surroundings is 2.79 kilojoules. Calculate the enthalpy change of the reaction that produces 1 mole of water. This problem is a bit more complex because the enthalpy change is asked per mole of water, not per mole of sulfuric acid. First, we write the balanced equation. Sulfuric acid is diprotic, so it will produce 2 moles of water when fully neutralized by sodium hydroxide. The problem asks for delta H naught for the formation of 1 mole of water. So, we'll write the equation with a stoichiometric coefficient of 1 for water. We divide the entire equation by 2. Now we have 0.025 moles of sulfuric acid reacting. From the 1 to 2 mole ratio, we must have 0.050 moles of NaOH reacting to produce 0.050 moles of water. We calculate delta H naught using the original Q value and divide by the moles of water produced, which is 0.050. We also need to multiply by the stoichiometric coefficient for water in our target equation, which is 1. Solving this gives an enthalpy change of negative 55.8 kilojoules per mole. The negative sign confirms the reaction is exothermic. Calorimetry is the experimental method we use to measure these heat transfers. A calorimeter is simply a device for doing this. We'll look at 2 main types: simple combustion calorimetry and solution calorimetry. In a simple combustion calorimetry experiment, a spirit burner containing the fuel is used to heat a known mass of water in a copper calorimeter. We measure the initial and final temperatures of the water and the mass of the fuel burned. Let's work through an example with propine. When 0.130 grams of propine is burned in excess oxygen, it heats 400 grams of water by 3.76 degrees Celsius. Calculate the enthalpy change of combustion for propine. First, calculate the heat absorbed by the water using Q equals mc delta T. Q equals 400.0 times 4.19 times 376, which gives 6,300 joules. Converting to kilojoules, Q is 630 kilojoules. Next, calculate the moles of propine burned. The molar mass of C3H4 is 40.07 grams per mole. Moles equals 0.130 divided by 40.07, which is 0.003244 moles. Finally, we calculate delta H naught. The question asks for the enthalpy change per mole of propine, which is the stoichiometric coefficient. We use the Q value in kilojoules and divide by the moles of propine. Delta H naught equals negative 6.30 divided by 0.003244, giving negative 1940 kilojoules per mole. A polystyrene coffee cup is an excellent simple calorimeter for solution-based reactions, such as neutralizations or dissolutions. Its low thermal conductivity reduces heat exchange with the surroundings, making it a good insulator. Let's work through an endothermic example. 200 grams of solid ammonium nitrate, N2,4NO3, are dissolved in 30.0 grams of water. The temperature of the water falls from 22.2 degrees Celsius to 17.5 degrees Celsius. Calculate the standard enthalpy change of solution for ammonium nitrate. Our system here is the ammonium nitrate and the water it dissolves in. The surroundings are the polystyrene cup and the air around it. The temperature change tells us about the energy change in the water. First, we find the change in temperature. 17.5 minus 22.2 equals negative 4.7 degrees Celsius. Notice the temperature change is negative, which is what we'd expect for an endothermic process. Now we calculate Q for the water. Q equals 30.0 times 4.1 times negative 4.7, which is negative 590 joules, or negative 0.59 kilojoules. The moles of ammonium nitrate are its mass, 2.1 grams, divided by its molar mass of 80.06 grams per mole, giving 0.025 moles. Finally, we find delta H naught. It's negative Q over N. So we have negative of negative 0.59, which is positive 0.59, divided by 0.22500. The standard enthalpy of solution is positive 23.6 kilojoules per mole. The positive sign confirms this is an endothermic process. Simple calorimetry experiments have inherent limitations that can lead to inaccurate results. A key limitation is heat exchange between the calorimeter and the surroundings. For fast reactions in a polystyrene cup, this is often acceptable. However, for slower reactions, heat loss or gain over time becomes significant. This means the thermometer won't record the true maximum or minimum temperature. To address this, we use a technique called extrapolation, also known as a cooling curve. The method involves placing one reagent in the calorimeter and recording its temperature for a few minutes before the reaction starts to establish a baseline. At a specific time, the other reagent is added, and the reaction begins. You continue to record the temperature at regular intervals. For an exothermic reaction, the temperature will rise rapidly, reach a peak, and then gradually fall back towards room temperature as the mixture cools. The problem is, the reaction is not instantaneous. Cooling begins before the reaction is complete. The temperature we record at the peak is lower than the true maximum. To find the true maximum, we extrapolate. We draw a best fit line through the cooling portion of the curve and extend it back to the time the reagents were mixed. The intersection of this extrapolated line with the mixing time gives us a corrected maximum temperature, Tmax corrected. This corrected temperature value is then used in the Q equals mc delta T calculation to determine a more accurate enthalpy change. Similarly, for a slow endothermic reaction, the temperature will drop, reach a minimum, and then rise again as heat flows in from the surroundings. We extrapolate the rising portion of this heating curve back to the mixing time to find the corrected minimum temperature. Calorimetry experiments are never perfectly accurate. It's essential to understand and account for the uncertainties involved. We can distinguish between two main types of errors: random errors and systematic errors. Random errors are unpredictable and cause measured values to differ slightly from the true value in an inconsistent way. They are typically associated with the precision of your equipment. We can quantify them using uncertainty analysis. For example, the uncertainty of a thermometer might be plus or minus 0.1 degrees Celsius. When you add and subtract values, like for calculating delta T, you add their absolute uncertainties. If your initial temperature is 20.0 plus or minus 0.1, and your final temperature is 30.0 plus or minus 0.1, then delta T is 10.0 plus or minus 0.2. The uncertainties add. When multiplying or dividing values with uncertainties, like in Q equals mc delta T, we add their percentage uncertainties. We calculate the percentage uncertainty for each value, sum them to get a total percentage uncertainty, and then convert that back to an absolute uncertainty for the final result. Systematic errors, on the other hand, are biases in your measurement that cause the results to be consistently too high or too low. They have a predictable effect. A classic example is heat loss in a simple calorimeter. The calorimeter is not perfectly insulated, so some heat escapes to the air. This means the water in the calorimeter does not absorb all the heat produced by the reaction. As a result, the measured temperature change, and thus the calculated enthalpy change, will be smaller in magnitude than the true value. This is a systematic error. So if the literature value of an exothermic reaction is negative 1367, but your experiment gives you negative 810, the significant difference is likely due to a systematic error like heat loss. The percentage error, calculated as the absolute difference relative to the true value, would be 40%. Understanding these uncertainties is a key analytical skill in IB chemistry. It's not about getting the right answer, but about evaluating how valid and reliable your results are. Now let's work through a full IB-style calorimetry problem that incorporates many of the concepts we've discussed. Consider the neutralization reaction between sodium hydroxide and hydrochloric acid. A student measures 20.0 cubic centimeters of 2.0 molar sodium hydroxide solution into a polystyrene cup. They record the temperature of the solution every minute for 3 minutes. At the 4th minute, they add 25.0 cubic centimeters of 2.0 molar hydrochloric acid, also at the initial temperature. They continue recording the temperature for several more minutes. The results are shown in this table. We can see the temperature is constant at 23.0 degrees Celsius for the first 3 minutes. At the 4th minute, the acid is added and the temperature rises to 34.0, then peaks at 34.5, and then begins to fall. Our task is to plot this data on a temperature time graph, extrapolate to find the maximum temperature change, and then calculate the enthalpy change of the reaction. First, we plot the points from the table on a graph with time on the x-axis and temperature on the y-axis. Next, we extrapolate. We draw a best-fit straight line through the baseline points from time 0 to time 4. We then draw another best-fit straight line through the cooling points after the peak. The intersection of these two lines gives us the extrapolated maximum temperature. In this case, it appears to be about 35.0 degrees Celsius. The initial temperature was 23.0. So our corrected temperature change, delta T corrected, is 35.0 minus 23.0, which equals 12.0 degrees Celsius. Now we have a more accurate temperature change to use in our calculation. Let's complete our calorimetry calculation. We have our corrected temperature change, 12.0 degrees Celsius. We need to find the mass of the solution and the moles of reactants. The total volume of the solution is 20.0 cmm3 of NaOH plus 25.0 cmm3 of HCl, which equals 45.0 cmm3. We make a common assumption in these dilute solutions, that the density is the same as water, 1 grams per cubic centimeter. So, the mass of the solution is approximately 45.0 grams. Now, we can calculate the heat energy absorbed by the solution, Q. Q equals mass times specific heat capacity times corrected delta T. Q equals 45.0 times 4.1 times 12.0, which is 2257 joules. This is 2.26 kilojoules. Next, we need the moles of the limiting reactant. Let's calculate the moles of each reactant. Moles of NaOH equals its concentration of 2 whole molar times its volume of 0.0200 decimeters cubed, giving 0.0400 moles. Moles of HCl equals its concentration of 2 whole molar times its volume of 0.025 decimeters cubed, giving 0.0500 moles. From the balanced 1-to-1 stoichiometry, the limiting reactant is NaOH, as there is less of it. We will use 0.0400 moles to calculate delta H naught. Finally, we calculate delta H naught. It's negative Q over moles of limiting reactant, multiplied by its stoichiometric coefficient of 1. Negative 2.26 kilojoules divided by 0.0400 moles gives us a standard enthalpy of neutralization of negative 56.5 kilojoules per mole. The literature value is negative 57.9 kilojoules per mole. Our experimental value is close, demonstrating the effectiveness of the extrapolation technique. We have now covered the core concepts of enthalpy and calorimetry. Let's recap the learning objectives we set at the beginning. We have successfully defined and differentiated between heat and temperature, explaining their roles in energy transfer. We learned to classify reactions as endothermic or exothermic and to interpret potential energy profiles to visualize the energy changes. You can now apply the key equations. Q equals mc delta T and delta H equals negative Q over N to calculate heat and enthalpy changes. And finally, you have seen how to analyze calorimetry data using extrapolation and to understand the impact of errors on experimental results. These principles are foundational for all of thermochemistry, from Hess's law to bond enthalpies. Need more help? For expert tuition in IB, A-Level, and IGCSE curricula, contact our tutors. Now, let's challenge ourselves with a series of IB-style practice questions. I will present each question, and then we will walk through the full detailed solution. Question 1 asks us to calculate the heat energy transferred when 120 grams of methanol are cooled from 65 degrees Celsius to 20 degrees Celsius. The specific heat capacity of methanol is 2.14 joules per gram per Kelvin. We use Q equals mc delta T. The mass is 120 grams. The specific heat capacity is 2.14, and the temperature change is 20 minus 60, which is negative 45 degrees Celsius, or negative 45 Kelvin. This is negative because heat is being removed. Plugging in the values, we get Q equals negative 11,556 joules, which rounds to negative 11.66 kilojoules. The negative sign correctly indicates that heat is being lost by the methanol. Question 2 gives us a combustion reaction and asks for the balanced equation and to sketch the potential energy profile. For part A, we balance the combustion of octane. With 8 carbon atoms, we need 8 carbon dioxide molecules. With 18 hydrogen atoms, we need 9 water molecules. This requires a total of 8 times 2 plus 9, or 25 oxygen atoms. Since oxygen gas is diatomic, we need 25 over 2, or 12.5 molecules of O2. For part B, since combustion is an exothermic process, the potential energy of the products will be lower than that of the reactants. The sketch would show the reactants at a higher energy level, an activation energy barrier, and the products at a lower energy level. Question 3 involves a dilution process. We need to calculate the change in temperature when 500 cubic centimeters of water at 10 degrees Celsius is mixed with 200 cubic centimeters of water at 80 degrees Celsius. This is a heat exchange problem. The heat lost by the hot water equals the heat gained by the cold water. We can set the heat lost by the hot water equal to the negative of the heat gained by the cold water. The heat lost is mass times specific heat capacity times the change in temperature for the hot water. The heat gained is mass times specific heat capacity times the change in temperature for the cold water. The specific heat capacity is the same for both and can be cancelled. Let Tf be the final temperature. For the hot water, the mass is 200 grams and delta T is Tf minus 80. For the cold water, the mass is 500 grams and delta T is Tf minus 10. The equation becomes 200 times the quantity Tf minus 80 equals negative 500 times the quantity Tf minus 10. Expanding and solving for Tf gives a final temperature of 37 degrees Celsius. This is a common method for calculating equilibrium temperatures. Question 4 combines our concepts with stoichiometry. We'll find the limiting reactant and calculate delta H naught. IB practice question 4. When 150 kg of powdered iron reacts with 25.0 Chem3 of 2.0 mol Dm3 copper 2 sulfate solution, the temperature of the solution rises from 22.0 dgC to 45.0 dgC. Calculate dT/dg for the reaction. Plus QSO4A FSO4A. We must find the limiting reactant first. The molar mass of iron is 55.85. Moles of iron equals 1.50 grams divided by 55.85, giving 0.0269 moles. Moles of copper 2 sulfate equals its concentration of 2.0 molar times its volume of 0.0250 decimeters cubed, which is 0.0500 moles. From the 1-to-1 stoichiometry of the balanced equation, iron is the limiting reactant, as we have fewer moles of it. Now we find Q. The total volume of the solution is 25.0 Cm3. Assuming the density is 1.0, the mass is 25.0 grams. Delta T is 45.0 minus 22.0, or 23.0. Q equals 25.0 times 4.10 times 23.0, which is 2404 joules, or tau 404 kilojoules. Finally, we calculate delta H naught using the moles of the limiting reactant, iron. Delta H naught equals negative 2.404 divided by 0.0269. This gives an enthalpy change of negative 89.4 kilojoules per mole. Our final question is a conceptual one, testing your understanding of the common sources of error in calorimetry. Identify 3 systematic errors that would lead to an experimental enthalpy change being less exothermic than the true value. Remember, an exothermic reaction has a negative enthalpy change. If the experimental value is less exothermic, its magnitude is smaller than the true value, closer to 0. This means that the measured value of Q, the heat transferred to the surroundings, was smaller than it should have been. Let's think of reasons for that. First, the most common error is heat loss to the surroundings, such as the air. If the calorimeter isn't perfectly insulated, some heat produced by the reaction will be lost to the room instead of being absorbed by the water. Second, the assumption that the specific heat capacity and density of the solution are identical to water is not perfectly true. The dissolved solute will slightly alter these properties, leading to an error in the heat calculation. Third, the heat capacity of the calorimeter itself, typically the polystyrene cup, is often ignored. The cup also absorbs some heat from the reaction mixture, but we don't account for this in our calculation, leading to an underestimate of the total heat produced. Other valid answers could include incomplete reaction, evaporation of the solvent, or the reaction not being at standard conditions. I hope these practice questions have helped solidify your understanding of these critical higher-level chemistry concepts. Thank you for watching.